Ever wondered how atoms, those tiny building blocks of matter, stick together to form everything around us? From the air we breathe to the water we drink, it's all thanks to the magic of chemical bonding. And today we're diving into the fascinating world of valence bond theory, or VBT for short, to understand the secrets behind these molecular bonds. So, buckle up, get your safety goggles on, because we're about to embark on a thrilling adventure into the realm of atoms and molecules. Let's start with the basics. Imagine atoms as tiny Lego blocks, each with little connectors. Chemical bonding is like snapping these Legos together to build amazing structures, except instead of plastic bricks, we're dealing with atoms, and the connectors are their electrons. Now, atoms are social creatures, and they love to share electrons to achieve a stable and happy state. This sharing, my friends, is what we call chemical bonding. Now you might ask, why is this sharing so important? Well, just like building a stable Lego tower requires the blocks to stick together, forming stable molecules requires strong chemical bonds. These bonds hold atoms together in specific arrangements, giving rise to the incredible diversity of substances we see in the world, from the water in our oceans to the DNA in our cells. So whether it's the air we breathe, the food we eat, or the devices we use, it's all thanks to the fascinating phenomenon of chemical bonding. Understanding this fundamental concept is like having a superpower that lets you peek into the hidden world of molecules and unravel the mysteries of the universe. One of the most common and important types of chemical bonding is covalent bonding. Think of it like this. You and your friend both want to play with a toy car. Now, instead of fighting over it, you decide to share. That's what covalent bonding is all about, atoms sharing their valence electrons, those outermost electrons, to achieve a stable electron configuration. This sharing creates a strong bond between the atoms, much like the bond of friendship formed over a shared toy. And just like friendships, covalent bonds can be single, double, or even triple, depending on the number of electron pairs shared between the atoms. More shared electrons mean a stronger bond. Just like spending more time with your friend strengthens your friendship. So next time you see two atoms holding hands, remember they're probably engaged in some serious covalent bonding, sharing their precious electrons to build a strong and stable relationship. Now, how do we explain this amazing phenomenon of covalent bonding? That's where our hero of the day, Valence Bond Theory, comes in. VBT provides a simple yet powerful model to understand how covalent bonds form and how molecules get their shapes. It's like having a secret decoder ring that helps us decipher the language of atoms and molecules. Imagine two atoms approaching each other, each with their own set of atomic orbitals, which are like little apartments where electrons reside. As these atoms get cozy, their atomic orbitals begin to overlap, like two friends merging their apartments to create a shared living space. This overlapping allows the valence electrons from each atom to interact and form a bond. It's like the two friends now sharing their belongings and creating a stronger bond through this shared experience. And voila, a covalent bond is born. Now let's dive a little deeper into this concept of orbital overlap. Remember those atomic orbitals, the electron apartments? Well, they come in different shapes and sizes, like apartments in a big city. And just like you wouldn't fit a king-size bed in a tiny studio apartment, electrons prefer orbitals that provide the right amount of space and energy. When two atomic orbitals overlap, they create a region of high electron density between the two nuclei, like finding the perfect spot in your shared apartment where you both like to hang out. This region of high electron density acts like glue, holding the two positively charged nuclei together and forming a stable covalent bond. The extent of overlap determines the strength of the bond. More overlap equals a stronger bond, just like spending more time in that shared sweet spot strengthens your bond with your friend. Not all orbital overlaps are created equal, my friends. Depending on how the orbitals overlap, we get different types of covalent bonds, each with its own unique characteristics. Think of it like building with Legos. You can connect the blocks in different ways to create different structures. The two main types of covalent bonds are sigma, and pi bonds. Sigma bonds are like the strong, stable foundation of a building, formed by the direct head-on overlap of atomic orbitals. They're like the main beams that hold the structure together. Pi bonds, on the other hand, are like the decorative elements that add strength and stability to the building. They're formed by the sideways, parallel overlap of atomic orbitals, like adding extra support beams to your Lego masterpiece. Now, sometimes atoms need to undergo a little makeover to form the most stable bonds. This molecular makeover is called hybridization, and it's like renovating those electron apartments to create the perfect living space for shared electrons. Imagine an atom with its orbitals in their usual arrangement. Now, to form the strongest bonds, these orbitals can mix and merge, like combining different rooms in your apartment to create a more spacious and functional layout. This mixing creates new hybrid orbitals that are perfectly suited for bonding. Hybridization is essential for explaining the shapes of molecules, much like renovating your apartment determines its final layout. It's like having a molecular interior designer that helps atoms achieve the most stable and aesthetically pleasing bonding arrangements. Let's take the example of methane, a simple yet important molecule made up of one carbon atom and 4 hydrogen atoms. Using VBT, we can understand how this molecule gets its tetrahedral shape and why it's so stable. Carbon, the central atom in methane, has 4 valence electrons, and each hydrogen atom has 1. To form 4 covalent bonds, carbon needs 4 half-filled orbitals. This is where hybridization comes in. Carbon undergoes sp3 hybridization, mixing its 1,2s and 3,2p orbitals to form 4 identical sep3 hybrid orbitals. These sp3 hybrid orbitals point towards the corners of a tetrahedron, each overlapping with a 1s orbital of a hydrogen atom to form 4 sigma bonds. This tetrahedral arrangement minimizes electron repulsion and gives methane its characteristic shape and stability. So there you have it, folks. Valence Bond Theory, with its concepts of orbital overlap, hybridization, and bond types, provides a powerful framework for understanding the intricacies of covalent bonding. It's like having a molecular toolkit that helps us predict the shapes, stabilities, and properties of countless molecules. From simple molecules like water and methane to complex biomolecules like DNA and proteins, VBT helps us unravel the mysteries of the molecular world. It's like having a superpower that lets us peek into the hidden workings of chemistry and appreciate the elegance and complexity of the natural world. So keep exploring the wonders of chemistry, and remember, the next time you encounter a molecule, think of the amazing dance of electrons and the elegant principles of valence bond theory that govern their interactions. Now you know how valence bond theory helps us understand the tiny invisible forces that shape our world. From the air we breathe to the complex molecules that make up our bodies, it's all about atoms sharing electrons to form those incredible chemical bonds. Keep exploring chemistry to uncover more amazing secrets of the universe. Remember, science is all around us, waiting to be discovered.